Alright, for this problem here, we have a figure skater spinning in place with an angular velocity of omega. And the figure skater brings in her arms, pulling them closer to her body, which causes her moment of inertia to decrease. And we want to find her new angular speed. So we're going to use conservation of angular momentum here. We know there were no net torques on our system, or really it's just the object here. But this is a case where it's just a single object changing its moment of inertia. So we're going to go ahead and substitute in our initial moment of inertia times our initial angular speed equals our final moment of inertia times our final angular speed. So initially, her moment of inertia was I and her speed was omega. After she pulls her arms in, her moment of inertia is now 3/4 I, and we want to solve for that final angular speed. The i's, of course, cancel out here, and we find that our final angular speed is going to be 4/3 times her initial angular speed. For B, we want to figure out the work done on the figure skater, so for that we're going to think about conservation of energy here. And we know that she's starting with rotational kinetic energy. There may or may not be some work done, but we're solving for it, so that probably is a safe bet. And we're ending with rotational kinetic energy as well. Alright, and so we can substitute in for rotational kinetic energy 1/2 I omega squared with our initial velocity and our initial angular momentum, or initial moment of inertia, and then 1/2 I omega squared for the final as well, with our final moment of inertia and our final angular speed. So this becomes 1/2 times I times omega squared, that was our initial, plus our work that was done, equals 1/2 times 3/4 I times 4/3 omega, that quantity squared. When we go ahead and do our math over here and square that of course becomes 16/9 omega squared, and we can cancel some things out and simplify here, so that cancels out part of that, that cancels out part of that, and what we're ultimately left with on that right side of our equation is 4/6 times I times omega squared. Okay, and so we can go ahead then and solve for this work term here, and we're going to find that our work is going to be 4/6, which is really 2/3 I omega squared minus 1/2 I omega squared. And we could go ahead and find a least common denominator. 4/3 is really 4/6 like we had before. This is really 3/6. And so we end up finding that our work done when we subtract those two is just 1/6 I omega squared. Part C here asks us what is the net torque acting on the figure skater, and the answer is there is no net torque. And that just comes from the fact that there's really no outside forces acting on the figure skater. So if we don't have any outside forces, or outside net forces, we obviously have gravity and the normal force, but if we don't have any other outside net forces, then there can't be a net torque acting on the figure skater. Therefore, the net torque is simply 0. On top of that, we use conservation of angular momentum here under the assumption that there was no net torque on the figure skater. If that were not true, then angular momentum would not be conserved. So if that's the case and there's no net torque acting on the figure skater, the question begs, why was there work being done? And the reason for the work being done, that really resulted from the force of the figure skater pulling her arms in. If you can imagine being in that situation and spinning pretty fast, your arms naturally are going to want to go out. So it's actually going to take force, it's actually going to take work from your body to pull your arms in closer, because naturally they just want to flail out when you're spinning really fast. And that's the reason why the figure skater ultimately gains some amount of energy, which we found in part B with our work. For this next problem here, we have a record that's initially spinning at a rate here of omega. It's just spinning by itself, and what ends up happening is a lump of clay is going to land on the edge of the record here, and that's going to ultimately cause it to spin at a new angular speed, and that's what we're looking for. So in order to solve this, we're going to set up conservation of angular momentum. Initial angular momentum equals our final. So initially, what has angular momentum in our system is just the disk. So the moment of inertia of the disk times that angular speed that we have for the disk is going to be equal to our angular momentum afterwards, which is the two objects together, so we're going to add their moments of inertia, times that final angular speed, which is what we're ultimately looking for. We're told here that the disk has a moment of inertia given by 1/2 mr squared. We don't know what the mass or radius is, so I'm just going to leave this here as 1/2 mr squared times our angular speed, which we're told is omega initially, and that's going to be equal to the sum of the moments of inertia. So we have 1/2 mr squared for the disk, and for the clay, two things. We're going to treat it as a point mass, so it's just mr squared, and we know that it's 1/4 the mass of the record. All right, so I'm going to say plus, for the mass of it, I'm going to say 1/4 m times r squared. Since it's on the edge of the disk, it's just going to be r squared times our final angular speed. So what we end up getting when we simplify here is 1/2 mr squared times omega, our initial speed, and that's going to be equal to 3/4, just combining these two fractions, mr squared times our final angular speed. We can see that the m's and the r squareds cancel out, and when we solve for that final angular speed, it ends up being 4/6 omega, which simplifies here to 2/3 omega, so 2/3 of our initial angular speed. So we have one that actually relates to some things we talked about a little bit earlier in the year, and that is Kepler's laws. So if we think about a planet that's in orbit about the sun, the first question is what force creates a torque on the planet as it moves about the sun. And if we think about this, the only force acting on the planet is the force of gravity. However, if we're thinking about the sun here as our pivot point, all right, and we draw a line here from the pivot point to the planet, R, we find that the force and the radius are either in the exact same direction or the complete opposite direction, meaning that the angle is 0 or 180, and there is no torque. Whenever the force acts on the pivot or along that radial distance, like we have right here, no torque is going to be created. So the sun, through the force of gravity, exerts no torque on this planet. The second question asks about Kepler's second law, which tells us that planets travel faster when they're closer to the sun. Okay, so they're traveling the fastest in here and the slowest out here. We talked about that before. Our planets sweep out equal areas in equal time. And we want to explain this using concepts related to angular momentum. All right, and so I think the easiest way to think about this actually is using our way of finding the angular momentum from the linear momentum, RP sine of theta. We can see that our radius, our distance from the pivot, and our angular momentum are inversely proportional. So if we're in a situation where angular momentum is conserved, and we are because there's no torque on the planet, that means that as the radius decreases, the momentum increases, and the object's traveling faster. Mathematically, we could say that the radius and the linear momentum are inversely proportional to each other. All right, for this problem here, we have a ball of clay that's initially moved at some speed, and it lands on a disc and sticks to it, and then the clay and the disc system begin to rotate. And so we want to think about what is the angular speed of the system afterwards. This is a collision. This is a collision that involves angular quantities. So we're going to use conservation of angular momentum. So initially, we're going to have the angular momentum of the clay. And we have two ways of finding that. We can do I omega using its moment of inertia, treated as a point mass, times its angular speed. But because I know the mass of the disk and the velocity of the disk, I'm going to use our other definition, which is RP sine of theta, that depends on the linear momentum of it to allow us to find the angular momentum. So initially, the momentum, the angular momentum of our system, is just going to be from the clay. So the radius for the clay times the momentum of the clay times sine of theta. Afterwards, the two objects stick together, so we're going to use this definition now because we're ultimately solving for the angular speed and because they're rotating. And so it's going to be the moment of inertia for the clay plus the moment of inertia for the disk times the angular speed of that system. I can substitute in the things I know. The radius here for my disk is just r, so I can just leave this as r here. The momentum for my disk is going to be the mass, or the momentum for the clay is going to be the mass of the clay times the velocity of the clay, and the angle here is going to be 90 degrees because I see when my clay hits the disk, there's my r, my velocity is going like that, and that forms a nice 90-degree angle there. And so that's going to be the angle between the radius and the momentum. So that's going to be equal to my system afterwards. So after the collision, all right, when it's the two objects rotating together as one, we're going to combine their moments of inertia. So the moment of inertia for the clay is given by mr squared, m is just the mass of the clay, and r is how far it is from the pivot, which is the radius of the disk, plus the moment of inertia for the disk, which is given by 1/2 mr squared. And the disk has the same mass, so that's why we're just calling them both m. Obviously that won't always be the case, times the final angular speed. We can simplify a little bit on the left side. That sine of 90 drops because it's just 1. And on the right side, we're going to have 3/2 mr squared times our angular speed. The m's cancel out here. One of the r's cancels out. And what we're left with here is when we divide by 3/2, it's like multiplying by 2/3. So we're left with 2v over 3r as our angular velocity here. For part B, the scenario is the radius of the disk is doubled, but the mass and initial velocity remain the same, and we want to know what effect that has on the angular speed of the disk. So everything else has stayed the same except for this r term here, which shows up a few times in our previous equation. And to answer this question, I'm really going to focus on the equation that we just derived in A. And so what I see here from this equation is that the angular speed and the radius are inversely proportional. So that means that if our radius is doubled, okay, our angular speed is going to be half as much, okay, because of that inversely proportional relationship that they have. If we wanted to do this mathematically, we could do that as well. We could say omega prime, our new angular speed, is equal to 2v over 3 times 2r, which was just using this equation and substituting our new radius. And so we end up getting, I'm not going to factor out that 2, we end up getting 2v over 3r, our original, times 1/2. And so we see that our new angular speed is just 1/2 times omega, which was our original angular speed. Okay. The second question here is going to ask about how our angular momentum changes, the angular momentum of our system changes when we double that radius. And so what I'm really going to think about is I'm really just going to think about my initial angular momentum, which I have up here. The angular momentum of the clay, which we used our equation that allows us to find it from the linear momentum. And the reason why I'm thinking about that is I know that in both cases, even if the radius changes, the angular momentum is conserved. So the angular momentum of the system is the initial angular momentum. So that means that L, our initial angular momentum, is going to be RMV sine of 90, and that sine of 90 really goes away, so it's just RMV. Our new angular momentum, L prime, is going to be 2r, right, our new radius, times mv. And so we can clearly see that there's just this 2 term here, and that means that our new angular momentum is 2L. And that makes sense given what we know about angular momentum, because we can say that angular momentum is directly proportional to our radius, so doubling the radius will double our angular momentum.